Good morning and good afternoon. My name is Brent Halpern. I am the Scientific Director for the AI Horizons Network, and this is our second AI Horizons Network seminar. Today we have Pin-Yu.Chen from IBM Research. He's going to be talking about recent progress in adversarial robustness of AI models, which is an extension of his NeurIPS paper from 2018. Pin-Yu's an RSM, a research staff member at IBM Research in New York, or Cambridge, probably Cambridge, sorry.
Yorktown.
IBM Research AI, and working with the MIT IBM Watson AI Lab projects, and expertise in data mining, machine learning, signal processing, cybersecurity. The general format is we'll have everybody muted, and Pin-Yu will give his talk, and then we'll open the conversation for questions. Also, if you don't want to unmute yourself and ask your questions, there's a chat channel. The chat is a little speech bubble icon at the bottom when you mouse over the bottom of your screen. So with no further ado, Pin-Yu, please go ahead.
Okay, yeah, so Brent, can you hear me all right?
You are fine.
Okay, yeah, so hi everyone, nice meeting you. I'm Pin-Yu.Chen, and thanks Brent for the nice introduction and for the invitation. So I'm a research staff member based in Yorktown in New York. So today I'm going to walk you through our recent works on the area of adversarial robustness. So this will, as Brent mentioned, this will be an extended version of our certification work published at the new RIPS last year. But in order to help us motivate what the robustness certification is about, we will have a small detour to walk you through attacks and defenses and spend the last half of the section on robustness certification. Okay, so let's start with something fun. So if I were to give you this label and ask you to provide a label for this image, what would the people usually provide? Most likely you will say this is an ostrich. And this is also what AI says. It is an ostrich by AI model, identified by AI model as well. But the interesting thing is about this image. So what would this image be labeled, right? So human would probably say, hey, it's also an ostrich. But the interesting thing is now AI says it's a shoe shop. And this is not a coincidence. So it turns out like these AI models can be easily fooled by this we so-called adversarial images. So you can not only turn a label of ostrich to shoe shop, it can be turned into safe or vacuum or whatever label you want. And the AI model we are talking about is not some random and crappy AI model. This is actually the best image classifiers using neural networks that we are using nowadays. And one thing I would like to highlight is that images and neural network models are not the only victims to these adversarial inputs. We are interested in images because it's easily to be visualized, and we are interested in neural networks because they are the state-of-the-art models for this task, for example, object detection. If you are working on other domains, you can certainly take other models into consideration and study their adversarial robustness. So these images, as I mentioned, is called the adversarial examples. So these are like prediction evasive samples that are being created at test time. Like you have already a trained neural network model and you want to find adversarial perturbations to that input such that the prediction of that model will go wrong, but the adversarial input are still look alike as the original input. And as some of you might know, I'm a big superhero fan. So there is always an episode in this superhero movie where you have characters that look totally the same, but one is like benign and one is evil, and then they look totally the same, but they have different characteristics. So I think this is a perfect analogy for adversarial examples. They look totally alike as a benign input, but their prediction and their output will be totally different, and they will have different functionalities. So why do we care about adversarial examples? So as I mentioned, this adversarial robustness is a big umbrella, and you can think about this robustness from different angles. For example, in addition to adversarial robustness, people also care about robustness of the training data. For example, if your adversary can have access to your training data and embed some backdoor to your training data such that the model you train on this poison data could be affected, then it is also a type of adversarial attack that we call the poisoning attack. But here we are more interested, in this talk, we are more interested in adversarial examples, which is the attack that is being deployed at test time. You don't have access to the training data, and instead we are facing a trained AI model at test time, and you want to create some prediction evasive adversarial inputs to that training data. And this is a typical scenario where we deploy AI models, machine learning models, systems as a service, right? So like a Google Cloud service, like IBM services, and so on. And whether and we are now asking whether you can find the vulnerabilities of these deployed systems. And by the way, let me know if you have any questions, and just unmute yourself and let me know by any time. So why do we care about these adversarial examples? So there are several reasons we have to deal with it carefully. The first thing is there is a crisis in trust. So like general audience seems to be very concerned if any inconsistent decision making between AI and machine learning models will exist. So this is, for example, a typical example is it possible to manipulate a stop sign by adding some adversarial stickers such that your autonomous driving car, when it sees this perturbed stop signs, it will think it's a speed limit, and hence it wouldn't stop, and causing some security-related issues. If you are a machine learning researcher, we are very interested in knowing why these machine learning models are so vulnerable to these small perturbations happening at the input space. So and because this somehow indicates there is a limitation in our current machine learning systems and how we train these machine learning models to do their jobs. And lastly, in terms of company or public awareness, there is always a concern about loss in revenue and reputation. For example, just like two weeks ago, you might find some articles saying Tesla's autopilot system can be easily fooled by just adding some small stickers on the road sign, and the autopilot system will direct you to a different route that is supposed not to do that. And like recently, last year, some Google online service accidentally tagged African Americans as gorillas, and kind of arise some discussions and leads to some revenue and reputation loss for these AI-based services. But we know as a fact that these things could happen either by the bias of the data, or it can be manipulated by these so-called adversarial examples. So if the general audience didn't know this technique exists and didn't know how easy we can manipulate the output of our AI model, then we can certainly create these adversarial images and causing some revenue or reputation loss or distrust among humans and machines. That's something we certainly want to avoid. So as I mentioned, this is what IBM's strategy is, and that's why we are very dedicated to this trusted AI. So trusted AI is our company's strategy, and among trusted AI, there are different pillars, including robustness, things that we just talked about, not just for adversarial examples, but also training time attacks, model stealing, and so on. And we also care about fairness. How do we make sure the decisions made by models are fair and justifiable? And we also care about explainability. How did you explain AI's models the decision? Why you think this is ostrich and why it is not some other labels? And we also care about accountability to make the AI models transparent. So this is the big umbrella under trusted AI, and robustness is something we are going to zoom in, and then we are going to have a deep dive to these certification methods. So I would like to show our portfolio in the research of adversarial robustness research. So this is apparently not an inclusive list, so I'm only highlighting the researches that I'm involved in. So if you count the whole IBM team, we have like probably double number of papers or technical reports working on this field. And I'm also focusing on adversarial examples on this slide. But I would like to mention we have done a lot of amazing works in other type of adversarial attacks as well. For example, to detect a poisoning attack, like training time attacks, the team at the IBM Alma Research Lab actually won a Best Paper Award at the Safe AI this year. So we certainly have a lot of visibility here. And in terms of research, we have published more than 15 papers on this topic of adversarial robustness. So we are certainly one of the most active and I would say leading group in this field. And we cover a lot of different topics, including attacks, defenses, robustness certification evaluation, connections to interpretability and robustness accuracy trade-off, and also some zeroth order optimization techniques to make this vulnerability analysis easier. And our research certainly have a lot of attention from the general public as well. So media will cover our research because this is not an interest not just to our research community, but to a general public as well, because AI models one day they are going to be coexist with human, being widely deployed to our daily lives. So this kind of research is very important, not to researchers but also to general audience. And we also have IBM has an open source toolbox called Adversarial Robustness Toolbox, where we release our public publications and codes to help people do this research in adversarial robustness research. So here is the roadmap of making AI or machine learning model trustworthy. And as I mentioned, there are many topics under adversarial robustness. So there are attacks, how you find the vulnerability of your AI models. There are defenses, how do you improve the robustness of your AI model and also detect adversarial inputs. And certification evaluation, basically how did you certify your model and your input is robust or not, and how did you provide a formal evaluation of the robustness of your AI model. And there is always the interpretability angle of adversarial examples, because eventually the existence of adversarial example can be explained by lacking interpretability of our AI systems. And for example, my colleague Sijia Liu is an expert in this field. There are a lot of research skill sets and tools that can be used to study adversarial robustness, including a lot of optimization techniques, robust optimization, high-dimensional statistics, and of course deep learning. So when I working on this adversarial robustness, I like to think of this research as a magic mirror. So basically, every researcher will see some part of it when you are looking at the papers on adversarial robustness, because it is a very young and exciting field, and it's a very inclusive field in the sense that every model we are working on, every task we are working on, we must have a model to execute these tasks. And whether this model is robust to these adversarial attempts is of our interest. So basically, adversarial robustness research is everywhere and is very comprehensive. So one thing that we discovered at first place, and it is honestly quite shocking for us, is that the accuracy does not imply adversarial robustness. So if you are familiar with the research of deep learning, you might know this very well-known competition called ImageNet. So basically, ImageNet is where people submit models to predict object detections, and then basically rank each model's performance in terms of their test error or test accuracy. So for the past few years, the only goal to benchmark each model's performance is the standard test accuracy. So out of curiosity, we actually take 18 different ImageNet models submitted over time. And they have a different accuracy, and then we kind of rank them in terms of robustness. So the x-axis is the different models' accuracy, and y-axis is the robustness. So you can think of the robustness that we are showing here is a measure of how easy it is to manipulate the input to generate adversarial examples. And somehow, to our surprise, we found that the more accurate models is actually less robust to adversarial examples, and this can be somehow explained in a sense that in order to achieving high accuracy, you more or less need to overfit the decision boundaries a bit and make a decision boundary non-smooth, and somehow this non-smoothness will cause adversarial examples to exist. So that's why we call it a robustness accuracy trade-off. And this also indicates in order to make this AI model trustworthy, accuracy is not the only metric. We should also care about robustness, because if you're solely pursuing a high accuracy model, it usually wouldn't come with robustness. So as I mentioned, why do researchers and society care about adversarial robustness? So overall, this is all about trust, because AI models and AI services are going to penetrate our daily lives in no time. But what's been discovered in this research of adversarial robustness is whenever there is a neural network model, there is actually a way to generate these adversarial examples. So I'm showing you other possible applications of generating adversarial examples. For example, this is the image captioning attack that we have shown in the past. So basically, this image will generate correct and related captions. For example, a red stop sign sitting on the side of a road. But again, if you use our technique and you add some small perturbation to create adversarial examples in the bottom, you can manipulate the outcome and having some like crazy captions like a brown teddy bear laying on top of a bed. And these two images are basically look the same to human. And you can do the same thing for automatic speech recognition systems, which we will revisit in a few slides. And these things did not just happen in digital world. In physical world, these things could happen as well. So CMU researchers have devised some adversarial glasses. So once you wear that adversarial glasses, your face recognition system will think you are someone else rather than the person wearing the glass. You can apply this technique to evaluate the robustness of autonomous driving systems for sure. And you can create these 3D adversarial objects, in this case, 3D adversarial turtles. And if you take your cell phone and take a picture from different angles, for most of the time, your machines wouldn't realize it is an adversarial turtle, and you will think it is a rifle or something else. So this adversarial robustness is not just happening in digital world. In physical world, people have been finding ways to make these things happen. And so you can imagine if our lives truly depends on these adversarial AI models to do jobs for us, there is a trust crisis that we need to resolve. Okay, so next I'm going to walk you through some adversarial attacks that have been developed in the past. So how do we actually generate these adversarial examples? So researchers actually start from a white box approach. So white box means everything is transparent to the adversary when you try to generate these adversarial examples, including how your model's architecture is, how your model is trained, how many, so basically there is no secret to hide from an adversary. So here, this is an example of showing you how do we generate adversarial example of a French bulldog. So if you input this original image, French bulldog, your neural network classifier will say it's a French bulldog with 90% accuracy. But what if now I want to generate some perturbations to the input such that it will be classified as, let's say, basketball? So what people do is actually very easy. It's relying on the backpropagation of this neural network you are going to attack. So the way we do is, in order to generate this adversarial perturbation, we ask neural network to give us some directions to increase the confidence of being classified as a basketball and also decrease the confidence of being classified as a French bulldog. And we also want to make sure the perturbations are small such that the final adversarial image will look the same as the original image. And as you can imagine, this technique is very general and does not limit it to image classification alone. So basically, different applications relying on neural network, because you have this function of backpropagation, you can do these adversarial examples very easily in the white box setting. So here it's more like a mathematical definition of how people generate adversarial attacks, or more specifically, adversarial perturbations. So first, we have to define something that we call threat model, like what is the allowed perturbation to your input. So we have a perturbation delta confined to some distance metric or some semantic space relative to a given input x0. So semantic space, you can think of these semantic perturbations happening on x0 as well. For example, rotation, translation, change the lightning, and so on. And so the general attack formulation is we try to minimize the distance, basically preserve the similarity between the original image x0 and the perturbed image x0 plus delta. while ensuring the prediction of the neural network model of X0 and X0 plus tilde are different. So this is a typical setting for the untargeted attack where you want to find a delta that make the final prediction went wrong, but you don't specify which target you desire. And it's very easy to change your untargeted attack formulation to a targeted attack formulation where you want your prediction of the perturbed image to be a specific label. And there are several alternatives of this attack formulation. You can do minimize the distance plus some attack loss function. But basically, it's a surrogate loss function of the condition that the two predictions on the original image and the perturbed image has to be different. Or you can do minimize the attack loss function subject to some distance as a constraint. So you want to make sure the distance between the original image and the perturbed image are smaller than some epsilon distance. And here are some commonly used distance in the literature. So we start from the most easy and mathematically well-defined distance, for example, the LP norm-ball centered on X0. So in this case, the distance of between X0 and X0 plus delta really boils down to the norms of the deltas. And usually people consider different LP norms. For example, L infinity norm of delta basically means what the maximum perturbation allowed in each input dimension. L2 norms are basically the sum of square differences of each input dimension. And L1 norms are their total variation, and L0 norms are the number of modified dimensions. How many, for example, how many pixels you will going to be modified. And more recently, our recent work have really pushed the limit of this attack by considering mixed norms and structure attack that focus on convolutional filters and so on, so we can generate a clean and interpretable perturbations. And that's how we can build connection to interpretability as well. And for the loss function, attack loss function, usually people use cross entropy or constructive loss. So constructive loss is something I explained in a few slides ago. For example, in order to make this bagel image to be classified as a grand piano after adding this noise, you will try to increase the confidence of the grand piano and also try to decrease the confidence of the bagel label. That's how people generate adversarial examples in a mathematical formulation. But you may argue, so far we are talking about is in the white box attack sense where you have access to your model and you can do backpropagation. But what if in a practical setting when you deploy your machine learning model as a service, there is no way I tell you what my model is behind the service. So this is in actually a setting of AI or machine learning systems with limited access, and that's what we call a black box setting. So there was a time people believed this black box setting is actually robust to these adversarial perturbations because now you are not able to do backpropagation, and hence my model should be secured. But our recent work shows this is actually not the case. So it turns out that even without doing backpropagation, we can still generate these adversarial examples. And so our work published in 2017 is actually the first work that tried to make this attack more practical in a black box setting. So the way we did it is we tried instead of doing backpropagation, which is infeasible in this setting, we are actually trying to estimate the gradient instead of doing actual backpropagation, and such that using this estimated gradient, we can generate these adversarial perturbations and make a French bulldog being classified as a basketball or so, or making a bagel classified as a grand piano. And this gradient estimation is nothing but some finite difference method that we have learned in high school or in calculus. And more recently, in 2019, we have improved the version of this black box attack. So our previous method is great, but it usually needs a lot of queries to make this attack feasible. So for example, to make the bagel being classified as a grand piano, we usually need a million of queries from the machine learning model. So what we are proposing here is actually a more query efficient way of doing this. So we actually apply dimension reduction to make the number of queries more efficient, and we also have a newer gradient estimation technique to reduce the number of queries we need to find adversarial perturbations. So if you compare the first row and the second row, of these methods, you can see that the new method auto zoom reduces more than 80% of the queries while still giving you a similar adversarial images at the end. So this auto zoom is actually making this black box attack, or the way we call it, is an efficient way of evaluating the robustness of AI systems with limited access plausible. Here are some other more examples of how this auto zoom works on ImageNet. So basically, auto zoom can save millions of queries when compared to our first attack, the zoo attack. And what it's actually doing is using a few queries to find successful perturbations, and then using more queries to refine the perturbation such that the final image will be similar to the original image, but still having this adversarial effect. So now you may ask, so what we have discussed so far, we are actually assuming we know the confidence score of the AI model from a black box system in order to generate this adversarial example. Then the next question is it possible to generate these adversarial examples if I only give you the top one prediction of the model and I didn't give you how confident I am for the input? It turns out the answer is yes. So in our recent ICLR paper, we showed that even if you are giving me the label, the top one prediction, which is the least possible information you should be given to any regular user, it is still possible to generate these adversarial inputs. So for example, in this case, we have a snake image as the original input, and we want it to be classified as a cat. So what we are doing is we start from a cat image and gradually fine-tune our perturbation such that this image will be similar to the original image, but it will be classified as a cat. And we can do it in a very query efficient way as well. So as I alluded before, adversarial attacks are not only occurring in images, and it can occur in other, and not only limited to convolutional neural nets. So like recurrent neural nets can be vulnerable as well. And other tasks, for example, image plus text, the image captioning could be vulnerable to these adversarial attacks as well. If you follow the general principle of doing backpropagation and specifying how you are going to attack your model and specifying your threat model. So I would argue this is a more or less universal threat or a universal concern to machine learning researchers. No matter what data set you are using, what model you are using, there is an adversarial robustness angle that you should consider how reliable your model is to this type of adversarial inputs. Next, I'm moving to adversarial defenses. So compared to attacks, defenses are actually less well developed because it's actually a more challenging task than doing an attack, because what attack is doing is finding one adversarial input that breaks the prediction. But for defense, you basically need to find you basically need to defend all possible adversarial inputs. So this is really a worst case scenario, and that's why making this defense a very challenging task. And there are a lot of reasons why learning a robust model is challenging. For example, we usually don't have interpretability of what our AI model makes decision, and our training data could be noisy and biased. And also, when we design these AI models, these neural networks, we really don't have the notion of security or privacy or robustness in mind. So the current architecture that we are training on could be vulnerable to these adversarial inputs. And finally, this attack and defenses, they can both leverage these AI techniques we build on and try to improve upon each other. So for example, if you look at the history of this adversarial research, you will find a trend that people propose some defenses, and a few weeks or a few months later, other researchers find a way to bypass these existing defenses and claim them these defenses to be ineffective. So there is really an arms race between attacks and defenses, and more or less this is what makes this research a lot of fun. So where we are in terms of this adversarial defense. So first, the way we evaluate defense is actually we are allowing the defender to move first. That means a defense is robust only when it is known to an adversary but still cannot break it. So defender has to make the first move to make your model robust. And attacker makes the latter move where it sees how the defender is doing and try to see if there's a way to bypass the defense mechanisms that you apply on your model. So there are several attempts for defenses, for example, data augmentation, try to augment with adversarial examples to improve to retrain your model. So it helps, but did not truly solve the problem. And there are ways to improve the model robustness, for example, by changing the conventional model training from minimization to minimax training. Basically, it's called a robust training. So in addition to train the model parameters, in the meantime, we are also generating these adversarial inputs and giving them the corrected labels and ask your model to memorize these adversarial inputs somehow and correct them so you can learn a more robust model. So this approach is effective, but we also find it to be not scalable. And because of this minimax worst case training scenario, you are suffering from a significant drop in your test accuracy compared to conventional training. There are other ways like doing input transformation, doing correction, rectification, anomaly detection, but many of the defenses are bypassed by advanced attacks. So people have been also looking at other ways. So the one direction that we believe are more promising is actually using the diverse models, including model ensembles and model with randomness, to basically increase the cost of adversarial attacks. And later on, I will show some domain-specific defenses where we have some promising results. But one downside is these domain-specific tasks. These defense rules cannot be easily generalized to other domains. So here is a case study of how we try to detect this audio adversarial samples. So audio adversarial samples is, again, you add some small perturbation to your input audio file, and it could alter the transcribed results of your audio system. So the way we detect these audio adversarial examples is really leveraging the temporal dependency nature of the audio speech recognition system to find the discrepancy between benign and adversarial inputs. So the way we did it is we first pass the whole audio input to the system, and we obtain a corresponding sentence. Then we try to chop off the input sequence and only pass the chopped version of the sequence pass it through the system again. Then we compare the counterpart of this the whole sequence and the chopped sequence. So if you are a benign audio, then your chopped sequence and the whole sequence will more or less be similar in terms of this word error rate or character error rate. But if you are adversarial input, because your nature is to change the transcribed output, then we can expect that the word error rate of the chopped sentence and the whole sentence will be significantly different. And we can actually use this error rate as a statistic to distinguish benign adversarial inputs. And this heuristic actually turns out to be very effective. And this is because we know how this automatic speech recognition system works, and somehow we are leveraging domain knowledge of temporal dependency to build a detector and hence improve the robustness of the entire AI system. So robustness and improving robustness and detecting adversarial inputs are certainly possible, but in this case, we are really relying on some domain-specific knowledge. And therefore, one interesting question is how do we generalize this notion and kind of creating an automatic way of finding these domain-specific knowledges for different tasks in an automated fashion. That would be a very interesting direction to go. Okay, so finally, we are looking at the robustness and certification and evaluation. So the reason I motivate attack and defenses first is there are several ways to evaluate the robustness of your AI model. So one very typical way is people usually use a game-based approach where you specify a set of players. In this case, I can call a different attack function and different defenses and operate them on my model, and I can benchmark the performance between each attacker and defender pair. So this is a very reasonable approach, but the downside is this magical rank may be misleading, and there's no guarantee that your model will be robust to the attacks that you didn't perform on. So there's concern of not being able to generalize your defense or robustness performance to other attacks or future attacks. So that's why kind of motivate the second way of evaluating robustness. That is, we call it verification or certification. So in this case, we are not relying on attacks to evaluate robustness. Instead, we try to build an attack-independent certification for evaluating robustness. So in this case, what this approach can do is to provide a certificate for your model. But the downside of this approach is that the optimal verification is very difficult, especially for large neural networks. And I will do a deep dive in a few slides later. So geometrically, how do we understand how this verification works, and what does it mean in terms of these adversarial examples? So geometrically, if you think of these dashed lines as the decision boundaries learned from a neural network classifier, so if your input is in the middle region, you will say it's ostrich here, and if you go across the decision boundary, it will be classified as other labels. So the way we define robustness, the attacks is trying to push the image to the other decision boundary, to go across the decision boundary, so it will be misclassified as something else. But trying to keep the distance between the red line and red point and the black point small, so they will look visually the same. So attacks in this case is actually an upper bound on the minimum perturbation. So here we define the minimum perturbation as the smallest distance required to alter the decision of the input sequence. So in this case, the perturbation given by any successful attack is actually an upper bound of the minimum perturbation. And on the contrary, the robustness certification is actually the lower bound of the minimum perturbation. So eventually, we want to find the minimum perturbation of any given input, but that problem has already been proven to be NP hard. So instead, we try to find an efficient way of computing a lower bound of the minimum perturbation, and we can provide a certificate saying no matter how you perturb your image within this within this green ball, your top one prediction will be the same, which means your model will be consistent. The top one prediction of your model will be consistent no matter how you move your point in this green ball. So that's how the certification we are going to give for the remaining slides. So here is the overview of what's been developed in the past few years. So we have done a series of works along the line of robustness certification and evaluation, including the Clever and Fast-Lin and Crown and CNN Search. So these are like different versions of our robustness certification works, and it can support. So we are trying to make the functions more general and support different network models. So I'll go ahead to explain what we are doing for this line of work. So basically, when we are trying to certify a neural network model, you need to first give a trained neural network model, and then second, given a data input. So because different data input will have different minimum distortion, some may be close to the decision boundary, some may be further away. So this robustness certification is given in the input sample level instead of a model level. And then we can specify a threat model that we want to certify, for example, the LP norms between the perturbed image X and the original image X naught. So what we are asking is if you are allowed to modify the image X naught by adding some perturbation within this epsilon ball, will the top one prediction of the perturbed image be altered? So in this case, is it possible within epsilon ball perturbation? Is it possible to alter the label of ostrich to a shoe shop or a vacuum? So the way we did it is so now you are allowing your input to be plus and minus epsilon for each input dimension, and then basically if you are assuming your activation functions can provide some upper and lower bounds, assuming the upper and lower bounds are known at this moment. So you can have a lower and upper bounds on each activation function, and all we do is we kind of propagate this activation function, the bounds of the activation function layer by layer. So after layers operation, we can reach the upper and lower bounds of each class output. And then what we do is we are comparing the lower bound of the ostrich with the upper bound of all other classes. And if we can assure the lower bound of ostrich is higher than the upper bound of all other classes under this perturbation, epsilon perturbation, then we can guarantee there is no attack within epsilon ball perturbation that can alter the prediction of our model, and therefore you can have an epsilon certificate. And then the remaining task is basically how do you do a bisection on this epsilon to find the largest possible epsilon that give you this type of consistent decision-making certificate. Okay, so this thing is easy if we know the lower bound and upper bound of your activation function. So the next question, and that's actually the main task that our new RIPS paper is trying to solve, is how do we find these lower and upper bounds of each activation function in a very efficient way? So we know for a fact that most of the activation functions in neural networks, they are actually nonlinear. For example, hyperbolic tangent, ReLU, sigmoid, and so on. So it is not linear in nature. But in order to make our certificate efficient, we actually requires linear bounds on each activation neuron and over each layer. So what we end up doing is we actually try to provide linear bounds of each activation function. So in this case, for example, this is an example of a ReLU function where we can provide linear upper and lower bounds of this ReLU function. And we do it for each layer, each neuron and in each layer. So if we linearize the activation bounds in for each neuron, then end to end we can have a linearized neural network model, and we can propagate these bounds in a very efficient manner. So here is some small theory that basically shows what we are doing here. So imagine this Fj, F is your neural network classifier, and J is the Jth class. So if we do this linear bounding techniques, what we can show is that the actual output of your function Fjx can be upper and lower bounded by two linear functions, Fjl and Fjmu, where Fjl and Fju are actually the coefficient actually linear functions by themselves, and these layer coefficients are determined by these propagations over layers that we have shown here. And what we are showing here, this is another example of how we do linearized bounds for different activation functions. So in this technique, our technique, this crown can be applied to different general activation functions. So basically, you specify activation function, then crown will try to linearize different parts of your activation function and make sure these linear bounds can be efficiently computed and can be propagated from the input all the way to the output. Okay, so once we have that in mind, basically what we are doing here is, again, we are trying to provide a linear bound on the output of a neural network model, which is known to be highly nonlinear. But providing linear bounds is actually a good balance for us to efficiently do this certification framework. So, for example, if we specify the epsilons and we want to know under this epsilon thread model, is it possible to find adversarial examples? Then different methods actually have different ways of doing that in an efficient manner. For example, the earliest work, Fast-Lin, assumes that the upper and lower bounds have the same parameter, and crown kind of allows different parameter for the upper and lower bounds, and also extended to general activation functions, whereas Fast-Lin only considers ReLU activations. And our most recent work, CNN Cert, which is published at AAAI 2019, is actually some certification methods optimized for convolutional neural nets. So here we are really leveraging the convolutional nature of a convolutional neural network, and so we can represent the upper and lower bounds in terms of convolution operations and make the computation more efficient. So CNN Cert is basically some technique that we build upon crown. So it includes all the benefits of crown. So it can also support general activation functions, but it can also support other things that we haven't shown for crown. For example, CNN cert can provide support to different various building blocks. So I should have mentioned this robustness certification is a very challenging task. So whatever model you have, whatever layer you have, whatever new operations you have in mind, we have to catch up with the advance of this neural network architecture and provide the corresponding certification techniques. So this does not come for free. For example, for a network model consisting of different layers, including convolution layers, spatial normalization layers, residual blocks, or pooling layers, we literally need to define how do we do this, how do we find linear bounds for different layers and different operations, such that we can do this certification in an efficient way. And so CNN Cert is our latest version of this robustness certification tool. So it can supply not just for pure CNN, but also more advanced models like ResNet or LeNet. So this is the slide that we try to conclude what is the difference between CNN Cert and the previous works. So what CNN Cert is doing is it can provide general network architecture. So I would say it can support state-of-the-art machine learning architectures that usually includes spatial normalization, pooling, and residual blocks. And CNN Cert is relatively more efficient than cron or Fast-Lin because CNN Cert is really using the convolution operations on CNNs, and instead Fast-Lin and cron, when we are developing, we usually convert them back to multi-layer perceptrons. So so CNN Cert kind of avoids this conversion and makes things computation more efficient. So here is a comparison of the certification bunks. So again, we are testing this certification on different networks. So it's different layers and different activation functions, different depths, and so on. And we can consider them for different LP norms. So what we can show is that the bounds found by CNN Cert is usually larger than the existing methods. It improves from some percent up to, and can possibly go up to 20% because of the efficient certification techniques and general architectures that we have in mind. And it is also computationally more efficient. So because of this convolutional nature, CNN Cert actually saves a lot of computation time. Okay, so lastly, a different work from certification is Clever. That is actually the first work we developed for evaluating robustness. So Clever is, again, an attack-independent score, but instead of providing a certificate saying no attacks can alter the prediction within epsilon balls, it is rather estimated a score. So it is a score rather than a certificate in the sense that Clever did not provide a certificate, but it provides an estimate of the minimum perturbation of a given input to the closest decision boundary. So how did you use Clever or other certifications that we have in mind? The best use case that we are recommending is really the before-after robustness comparison. So more or less, you'll encounter a problem if I do a certain operation in my current model, for example, add a pooling layer, do some pre-filtering, how much robustness can I gain, right? So to answer that question, it's actually very ideal to use Clever or the verification techniques that we have discovered so far to do this job. So it provides a score or a certificate to justify how much robustness you can improve by doing a certain operations. And we also use Clever in other ways, for example, to understand the accuracy robustness trade-off of different image connect classifiers that I have shown you before. Within IBM, we actually extensively use Clever to do these interesting demos and so on. So one interesting demo we do is called the big check. So what we do for Clever is we kind of hypothesize 3 different banks using different classifiers to do this handwritten digit recognition, and we use Clever to compute their robustness scores and ask humans to rank this robustness and agreement between humans and machines. And more or less, we found out Clever score can reflect how people think the robustness of this AI banking systems as well. So it is a very interesting use case, and we have a demo on this link address. So if you're interested, feel free to check this out. So that's how Clever can be used. It can use to understand the robustness of different threat models, different data sets, different neural network architectures, or different defense mechanisms. We have open source Clever, so it's being implemented in the Adversarial Robustness toolbox. And in addition to Clever, ART has a lot of different attacks and defenses. So I would say it's the most comprehensive adversarial toolbox open source so far. So feel free to check it if you are interested in this line of research. Okay, so lastly, I would like to give you some takeaways. So hopefully by now I have convinced you that adversarial robustness is really a new AI standard for trustworthy machine learning system, because eventually when we deploy machine learning or AI models to the world, we not only want them to be accurate, but we also don't want them to make mistakes, especially these stupid mistakes. And I would consider these adversarial examples as a very stupid mistakes, considered by any human being. So how do we? So accuracy should not be the only goal for AI models. We should also consider adversarial robustness and make sure this AI model don't make these stupid mistakes, no matter it is unintentionally or maliciously being manipulated. And I also want to highlight this is a very interesting area because there's always on race between attackers and defenses. So attackers can use AI to generate more advanced attacks, and also defenders can also use AI to generate more advanced robust models. And we are very curious about what will be the equilibrium of these arm races games. And lastly, we also spend some time to discuss how do we formally evaluate and improve model robustness. And what I discovered so far is we have a Clever, basically attack-independent robustness scores. And I also tell you how we develop crowns and also a CNN cert, basically efficient ways to provide robustness certifications. And I would argue doing this certified robustness or evaluation is better than just coding some random attack functions to test your model, because that game-based evaluation is not certified, and you cannot guarantee your defense can be generalized to more advanced attacks. But certification or robustness evaluation can actually guarantee this robustness no matter what attacks you have been using. And the other good thing is you can use this certification or evaluation tools to compare your model's robustness before or after you implement some mechanisms to make it more robust. So eventually, I think the next thing that we are going to focus on, and also the trend of the whole research community, is to look into provable, certifiable, and scalable defenses. So as you can imagine, there is a lot of fun in this research area. And if you are interested, feel free to contact me or any colleagues within IBM that you know of and join us for this exciting journey. So this is indeed robustness, I believe, is an intersection of a human's perception, AI model, and also the data quality. So this is a very challenging but also very salient job that we need to solve. So I want to do a final acknowledgement here. So a lot of works, I have many amazing collaborators, and many of them I believe are on the phone now, especially my IBM colleagues. And we have these amazing collaborations between MIT and IBM, and also from AI Horizon Networks. So I would like to thank Lisa, David Cox for making this happen, and also from great support from my management chains like Payot and also Saska. And also a lot of collaborators for people who developed different attacks that we didn't really look into, for example, poisoning attack, and also developing this adversarial robustness toolbox, like Ian, Matthew, and their teams, and also Casey and their teams for making our demo possible. So if you have questions, feel free to reach out to me or find me on the Twitter, and that will conclude my presentation.
Thank you, Pin-Yu. Thank you very, very much. It was a great talk. Let's open up for any questions. Please unmute yourself. If you're not familiar with WebEx, if you move your mouse, you should see a little microphone and then click on it.
I have a question.
Go ahead.
Thanks, Pin-Yu. Great research. My question is about certification. One thing that has been bothering me about certification is the fact that you are actually certifying for a particular image rather than
Yes.
for the network itself.
Yes.
So my question is, do you foresee any way where we can actually get a different perspective that doesn't require you to provide an image? I'm specifically worried about images because potentially before you deploy a model, you don't know exactly the distribution of the data that you're going to receive. And so the images may be slightly different. So even though you have a certification for a very particular image, the results may not be consistent for more general distributions. So, would love to hear your thoughts.
Yes, I think this is a very legitimate question. But I guess there are some difficulties to make certification for the model itself at this point, because eventually these adversarial inputs are basically operated on a per sample base, right? So, and if you look at the decision boundaries, especially when we are considering certification for adversarial examples, these decision boundaries from a neural network model, they are already fixed. So it is basically impossible to provide certificate for any input because there must be some inputs that are very close to the decision boundary. So, but the next interesting question is, can we somehow, when we try to gauge the robustness in terms of models, or let's say in terms of per class, can we somehow create some representative samples, and such that by guaranteeing the certification on these representative samples, then this robustness can be brought up to a model level or the class level? I think that would be a very interesting question. But at this point, I don't think it is an easy task.
Okay, thank you.
Okay, other questions?
Hello, this is Liang Sha from RTI.
Hi.
So much for the great talk. This is really exciting. So I'm wondering if you could comment on some theoretical problems along this direction.
Okay, yeah. So I guess there are various theoretical problems that I can think of. For example, is robustness really at the price of accuracy, right? So empirically, we observe in order to make your model more robust, you always sacrifice test accuracy. But is that necessary, right? Oh, and if it's true, what is the theoretical explanation? What is the limit, right? How did you calculate this theoretical trade-off, right? And in terms of robustness, robust training, for example, this minimax training, people is already a challenging task for robust training for itself. Not to mention, we are trying to bring this minimax optimization to the neural network level. So how did you even sure minimax training on neural network will converge? And also, is there a scalable way of making this minimax training possible? I think there are various problems, and for example, then there are some fundamental problems that we don't know quite sure what are the answers. For example, why do these adversarial examples exist? And we don't really know. So there are, I think, a lot of open questions, and no matter what your expertise and your angle is, you must be able to find an angle to tackle this problem.
Mm-hmm. Yeah, and so sorry, just a very follow-up from my comments. It reminds me of like a smooth analysis.
Yes.
Like your input may have some noise, and then you are trying to build a classifier to fight against it, and focus on the kind of the mixture of worst case slash average case analysis. So that's interesting to look at.
Yes, exactly. So that's a very good point. So this smoothness actually relates to the input Lipschitz function. So if you think your neural network as a function, then its Lipschitz constant actually regulates how much your input perturbation will amplify the output. So, and that is something that we use to evaluate the robustness. Mm-hmm. That's a very nice observation. Yeah.
Thank you.
Okay, we're almost at the top of the hour. I don't want to cut off questions, but for those of you that have to leave, I want to remind you that our next seminar is Thursday, May 2nd at 4 p.m. Eastern Time, and it will be by Chen of RPI on bidirectional attentive memory network for question answering over knowledge bases. Okay, are there any other questions for Pin-Yu? Okay, any other comments? All right, I want to thank everybody then for attending. This was a really great turnout, even bigger than our first. and I hope to see you all again next week.
Thank you, Brent. Thank you, everyone.